Hello and welcome back to Data Analysis and Visualization. I'm Jivita Christie, and in this video, I'm going to talk about hypothesis testing. So let's begin. First of all, what is a hypothesis? A hypothesis is a proposed explanation, which is unproven, for a phenomenon. So for any phenomenon, if you have a proposed explanation, and remember that hypothesis is something that is just explained or suggested. It is not proven to be true or false. So that's what we are going to focus on in this video. Examples of hypothesis would be number one, if I eat less sugar, I will lose weight faster. This is a hypothesis. It hasn't been proven that whether this is true or false. This is what you prove using research and experiment. If I drink more water, I'll feel more energized. This is another example of a hypothesis. If we use this advertising slogan, will increase sales. So this is another hypothesis that if certain advertising slogan is used, then it might result in an increase in the sales. Testing or proving a hypothesis is a very important field of statistics and is immensely helpful in the business world. Now, how do we test a hypothesis? To take the hypothesis, if we change the color of the Add to Cart button on our e-commerce website, will increase sales. So remember, any e-commerce website that you go to, you'll find a cart button that you can click on whenever you decide that you want to purchase this particular product. So this button that you have on your website, the hypothesis says that if you change the color of that button, then that would result in an increase in sales. This is a hypothesis. It is not something that is proven to be true or false, but it is something that you would like to prove to be true or false. So to test this, first of all, you have to foresee a lot of problems that can happen. And we are going to see those problems now. So what if the change was carried out when the end of the month was approaching? That is when the sales were naturally going to increase. Now, end of the month is when people get paid, and that's why they are more likely to buy stuff. And that's why sales could just naturally increase. It may not be because you changed the color of the button. The second problem could be, what if the company increased ads around that same time? So what if you started advertising more for your e-commerce site, and that's why the sales increased, not because you changed the button color. Another problem could be, what if there was some random event that resulted in a chance in sales, that resulted in an increase in the sales. So this could be also, there could be any random event occurring because of which the sales increased. So you need to prove that your sales increased because of the hypothesis that that you changed the color of the cart button on your e-commerce site. So there are many difficulties while testing a hypothesis in reality, and this is one of the controversies that you might face in statistics. Now, how do we solve that? So to solve that, first of all, you need to define a null hypothesis. What is a null hypothesis? This describes the existing conditions or present state of affairs. Examples are, number one, all lilies have 3 petals. So lilies are flowers and they have 3 petals. So this is a null hypothesis because it's true in itself that all lilies are having 3 petals. This is the current state of affairs without you making the change. The second type is, the number of children in a household is unrelated to the amount of televisions owned. Now, this is again a null hypothesis because it hasn't been proven true or false, but we are not trying to research this topic. We are trying to research the impact of televisions, number of televisions in the household, and the number of children. So when we are trying to do a research on this, the null hypothesis is that both are having no relation at all. The third example could be changing the add to cart button on the e-commerce website will have no effect on the sales. So this is once again a null hypothesis, which is what we assume before we begin our research. Now, how do we frame a hypothesis for our statements? So for that, we need to have an alternative hypothesis, which is used to compare or contrast against the null hypothesis. So example is, if we change the color of the add to cart button on our e-commerce website, we will increase sales. That is an alternate hypothesis. The null hypothesis, if you remember, was that if we change the color of the add to cart button on our e-commerce website, it will have no effect on sales, either positive or negative, and that is the null hypothesis. Now we have changed this null hypothesis into an alternative hypothesis, which is that if we change the color of the add to cart button, it will increase our sales. So this was the null hypothesis once again, just for your reference, that users exposed to the new add to cart button did not change their tendency to make a purchase. An alternative hypothesis is that users exposed to the new button resulted in increased sales. So let's see how you can prove whether this alternate hypothesis is true or we should stick to the null hypothesis. So for this, we do a research design with a blind experiment, which is a common practice which is used in drug testing by pharmaceutical companies. And here we are going to design an experiment to investigate whether a new flu medicine reduces the length of time flu symptoms were experienced. So there is a new medicine for flu, and we want to find out if that medicine can cure flu or the symptoms of flu within a lesser amount of time than it would take if no medicine was taken. Okay, so this is the experiment, and in this experiment, we are going to take this setup. So the setup is we need a group of people, and let's say that they are about 80 volunteers. We will separate this population into two equal groups of 40. For the group 1, we'll call the group 1 a control group, where 40 volunteers will be given a fake pill. Now, these volunteers will not be told that they are given a fake pill. Okay, so they'll be just given a pill that does not do anything, but they will be told that this is a flu medicine. And there will be a group 2, which will be the treatment or experimental group, which also would contain 50% of the population, which is 40. And these people will be given the real pill. Now let's formalize our hypothesis. So the null hypothesis is this. Subjects taking the new flu medication did not change the duration of the flu symptoms compared to those who took the placebo, which means the fake pill. So null hypothesis says that both the control group and the treatment group, both of them, they all experienced flu symptoms for equal number of days, and that means the medication was not effective. The alternative hypothesis is subjects taking the new flu medication had the duration of their flu symptoms reduced compared to those who took the placebo, which means they took the fake pill. So people who are taking the flu medication, they experienced their flu symptoms for lesser amount of time than those who took the fake medication. So this is our hypothesis, alternative hypothesis and null hypothesis. And we have to prove that the alternative hypothesis is either true or false. Now, once again, there could be problems. Like we saw with the add to cart button, there could be problems that users are kept uninformed about the pill. In the blind experiments, users are kept uninformed about the pill they are taking so that we can avoid changes in the user behavior, right? So users are not told which type of pill they have, whether it's a fake one or the real one, so that you can avoid changes in the user's behavior. For example, if somebody is given a fake pill and they are already told that it's a fake pill, then they might try to attempt other remedies for their flu, right? They might try to take some other medicine, and that could affect your final results. If the users are already told that it's a fake medicine, then issues could be caused in the test when assessing the participants on whether or not they really have the flu or it is some other strain of the common cold. Okay. Persons who know that they are taking the pill, they might start to take less rest, assuming that the pill is definitely going to work, and that's why let's just start doing all the activities. And this could prolong or worsen the symptoms. And again, your experiment would not be fair, a fair experiment. Now, what is the statistical significance of this? Once we obtain the results from the two groups, how do we interpret that the results how do we interpret the results with any degree of certainty? So take a look at these results. Group 1, which is the control group, they had flu symptoms for 5.4 days. This is an average. So we took an average of all the 40 people in group 1, and their flu symptoms lasted for an average of 5.4 days. And for group 2, which was the experiment group, which was given the real medication, their symptoms lasted for an average of 4.8 days. So there is a difference. The group which was given the fake medication was 5.4. The one that was not given the fake medication, which was given the real medication, their symptoms lasted for 4.8 days. So there is a difference. But we need to find out if this difference is of any help to us, right? If this difference is actually making sense, does it have any statistical significance? Okay. So first of all, we begin by comparing our means. So the first group, the mean was 5.4. For the second group, the mean was 4.8. Our null hypothesis stated that x1 minus x2, that is bar x1 minus bar x2, would be 0, because null hypothesis said that the flu medication has no effect on how many days the people are experiencing, the volunteers are experiencing flu symptoms. So that's why the difference between those two means is 0. Now, for the alternative hypothesis, it is stated that bar x1 minus bar x2 would be greater than 0, because we want to prove that when somebody takes the flu medication, their symptoms, the number of days for which they experience those flu symptoms, are reduced, which means the mean of the second group would be less than the mean of the first group. And that's why the difference, which is x1 minus x2, would be greater than 0. And which is true in our case. 5.4 is greater than 4.8, and that's why 5.4 minus 4.8 gives us 0.6, which is greater than 0. So we are comparing the means first of all. Now, based on this, should our null hypothesis be rejected? So we need to ask a question first of all, is this going to happen every time? Okay, if we were to run this experiment several times, then each time we will be getting a new mean. Obviously, we won't be getting the same values each time, right? So we are getting all these values every time we are running this experiment. So sometimes we are getting a value which is less than 0.6. Sometimes we're getting a value that's more than 0.6. So would this be happening every time that x1 bar x1 minus bar x2 is greater than is going to be greater than 0? Is this going to happen every time? This is the question that we need to answer. If we can answer this question, we can say whether or not to accept the hypothesis or reject the hypothesis. To do that, we have to perform a permutation test where each time we will redo this experiment, and that's known as a permutation test. We do this so that we can calculate a distribution of the test statistics for each trial or iteration of this experiment. So we want to perform this experiment several times so that we can compare the means afterwards and know for sure that this is going to happen many times. And this is what we call sampling distribution. So what exactly is sampling distribution? So our sampling distribution approximates a full range of possible test statistics for the null hypothesis. And then we can compare our control group mean to see how likely it is to observe this mean. Okay, 5.4 was a control group mean, which means that was the average days people experienced symptoms without taking the real medication. So we have to compare all our test results with this. And we do this by rerunning our control group test several times and observing whether the mean of 5.4 is likely or rare. Now, it's not as simple as it sounds. Can we run the simulation of retrials like that? In the real world, we cannot do that because there are lots of problems like time or money and a lot of other constraints. So we cannot run the same experiment that many times. So what do? We don't need to do that. There's a trick to it. So consider this. The red ones are volunteers in the control group. The green ones are volunteers in the experiment group. Now what and this is what the original result looks like. This is the original result. Okay, you can see in this table, what this table actually shows is number one is the first subject, the first volunteer. The first volunteer was put in the control group, that's why it's red, and he or she experienced symptoms for about 4 days. The second volunteer was also in control group and experienced symptoms for 2 days. The third one was in experiment group. That means this person was given the real medicine and he or she experienced the symptoms for 3 days. So and so on. Like that, we have a list of our original results for all 80 volunteers. Now, what should we do to run this experiment again? We are supposed to perform a retrial. Okay, so to do the retrial, we take some of the individual data points and randomly assign them to the other group. And then we calculate the new mean after this randomization. So what we do is we mix these red and green dots that you see. That means we take some volunteers from the control group, put them in the experiment group, and we take some volunteers from experiment group and put them in the control group. While doing this, we have to make sure that the number of volunteers in each group still remains 40. Okay. So this is what we have done. The first volunteer we have shifted from control to experiment, and the third one we have shifted from experiment to control, and so on. So we are randomly going to just move the data points from one to another group. And then we will run the experiment again. We'll try to calculate the mean values again. And once we have calculated the means, then we will record those means. We'll record the mean values average for all these simulations that we are running. Okay, we log the mean difference, and the mean difference is our initial mean minus the mean of the randomized trial reassignments. So once we have reassigned all the means, then we are going to, once we have reassigned all the volunteers, we'll run the experiment again, calculate the mean, and note down the mean difference, which is 5.4, which was the original one, subtract that from these randomized trial means. And this way we create our sample distribution. So after we have done this, we are going to perform some testing, which is a hypothesis test, which I'm going to talk to you about in my next video. So I'll see you there, and thank you for watching.